My talk is based on joint work with Malte Gerold, preprint from 2018. While this preprint follows somehow the historic order of the definitions in order to capture in particular the people who worked on interacting Fock spaces already. For this audience here, I opted to do the opposite. So the definitions will be in the anti-historical order. So I start, therefore, with the Hilbert space version of interacting Fock space. This is just a graded Hilbert space. So direct sum over Hn and natural numbers, 0 included. They are referred to as n particle sectors. And in particular, the 0 particle sector is required to be generated by a single unit vector omega, which is usually called the vacuum. And a space of operators on this space, bounded for now, such that what the set A star generates out of Hn is Hn plus 2. So this is degree 1 operators, and you can get everything by successive application of the these are referred to creators, the elements of the set, by applying creators to the vacuum vector. We may analyze the operator algebra, the Banach algebra generated by this set. This is usually going under the name of tensor algebra. And we may look at the C-star algebra generated by this set of operators. And this is usually under the name of Köblitz algebra. And we may ask what these operator algebras tell us about the structure of the interacting Fock space. As an example, Davidson, Ramsey, and Shalit have analyzed these operator algebras as they emerge from finite dimensional commutative subproduct systems. And Kakariadis and Shalit have done this in the non-commutative case. And for instance, the non-self-adjoint operator algebras do classify the interacting Fock spaces in this subclass, while the star algebras don't. So there are definitely interesting questions for other classes of interacting Fock spaces around. And in general, we can always embed in several ways these operator algebras into, in the non-self-adjoint case, tensor algebras in the sense of Julian-Solel, and in the self-adjoint case, Pimsner-Köblitz algebras over suitable C-star correspondences. There are several ways to do this. Minimals, maximal. This I cannot explain in little time. One of our results about interacting Fock spaces is that they embed into a usual full Fock space. And the creators on this usual full Fock space are given by the usual creators on this full Fock space, modified, squeezed by some degree 0 operator. This reminds a bit of weighted shifts. Baruch Solel surely could tell more about this. However, even if we start with bounded sets of operators, or sets of bounded operators, better, the kappa classifying these things here can be unbounded. So if we restrict to bounded operators, also kappa bounded, then we are definitely losing something, even if we are interested only in bounded operator algebras. Therefore, it's essential that we model our theory for pre-Hilbert spaces. The algebraic direct sums and tensor products are all algebraic. And in particular, we look at the algebraic full Fock space. So the definition adapted to this setting is the following. An interacting Fock space is given by a family of pre-Hilbert spaces as a direct sum, and a set of operators such that the algebraic span of Hn gives Hn plus 1. So no completion here. And of course, if you look back at the previous slide in the Hilbert space case, we just replace the Hilbert spaces with what the nth monomials within our creators generate algebraically out of omega. Then because the operators are bounded, we get dense subspaces of our Hilbert spaces. So we do not lose anything by this algebraic setting. So let me go one step back in the history and look at the definition of an interacting Fock space based on another pre-Hilbert space H. This is just an interacting Fock space as before, together with a linear surjective creator map from the pre-Hilbert space onto our space of operators, of creators. The idea is that a basing relates our interacting Fock space to a full Fock space. And be aware, this is all algebraic here. In fact, every based interacting Fock space comes along with a canonical surjection from the full Fock space onto our interacting Fock space. Omega goes to omega, and simple tensors go to the corresponding product of creators applied to the vacuum. This lambda is what we are going to call a Fock map. By Fock map, we mean an even vacuum preserving map. Every interacting Fock space can be based. Just take any inner product on the vector space A star, and for little a star, choose the identity map on A star. This is even injectively based, meaning that A star is an injective map. And the basing can be done well, and it can be done not so well. All interacting Fock spaces that occurred so far came with a basing. They came as interacting Fock space based on some pre-Hilbert space. And the importance of the new definition is to give us the freedom to go away from a bad basing and choose a better one. Now, a property we are definitely interested in is that our interacting Fock space based on H be embeddable. By embeddable, we mean that there is an isometry from the interacting Fock space into the full Fock space, but not the algebraic full Fock space, rather its completion. That's important. To have some functional analysis here. An interacting Fock space can be based non-embeddably. Just make sure that the orthogonal dimension of the completion of H1 is strictly bigger than the infinite orthogonal dimension of the completion of H. Then this will not be embeddable. But this is the only obstacle that can occur. So by changing our basing, we get something better. And the theorem is every interacting Fock space can be embeddably based. I cannot tell anything about the proof, but let me mention this little stupid lemma here. If a Hilbert space is generated by a subset S, then the dimension of the Hilbert space, orthogonal dimension, cannot be bigger than the cardinality of the generating subset. And despite this looks pretty much obvious, we found it difficult to prove. Therefore, I like to mention it. Okay, why are we interested in that our based Fock space is embeddable? We have our canonical surjection capital lambda. I should say this capital lambda encodes already all the information we can have about the interacting Fock space. In particular, what are the creators and so on. And by the isometry, the embedding, we sent it back to the Fock space. So the composition is a map, little lambda, that goes from the algebraic Fock space into the completed Fock space. And it captures everything we can know about our interacting Fock space. So we are back in the usual full Fock space. Like every isometry that takes values in a Hilbert space, it has a densely defined adjoint. Send back the range to where it comes from and set the rest 0. Important is that if we are in a Hilbert space, this is a dense subspace. Also this here, if this is dense, then also this subspace here is dense. So we have the theorem is we get a unique Fock map from this domain here to the other dense subspace, such that first of all, conjugation with the isometric psi makes sense. This is thanks to these weird definitions here, domains and codomains. So conjugation with the isometry sends a creator on the interacting Fock space to the usual creator on the full Fock space, squeezed or modified by this operator kappa. Of course, this is an algebra monomorphism, and if the creators happen to have adjoints, it's even a star algebra homomorphism. Moreover, lambda and kappa are related by this formula here, and if we write it down in particle vector-wise, we get a recursion for lambda. The recursion has a unique solution, namely this formula here for lambda. Of course, lambda and kappa n are the restriction to the n particle sectors. Okay. Now, not every kappa is possible in this way. Kappa is, by the properties stated, is onto the image of our interacting Fock space in the full Fock space, and it is 0 on this subspace. But this is all it needs to be a good kappa. If we have a pre-Fock subspace of our completed full Fock space, this means we have a direct sum over pre-Hilbert subspaces of the completed tensor powers here, of course the vacuum, and we define the same sort of dense subspace here, then a squeezing relative to this pre-Fock subspace is a Fock map from this domain into this dense subspace that is onto I and 0 on this subspace. And every squeezing for I turns I into an interacting Fock space based on the Hilbert space H, pre-Hilbert space, sorry. And it is already embedded via the canonical embedding of the subspace. And a little lambda and the capital lambda coincide. So we have identified a Fock space sitting already in interacting Fock space, sitting already in the full Fock space. And we call such an interacting Fock space a kappa interacting Fock space. By what we just did, so every Fock space can be embeddably based, hence embedded. If it is embedded, there's a kappa describing it. So every interacting Fock space is isomorphic to a kappa interacting Fock space in the sense that there is a Fock unitary between the two that intertwines the creation operators. And if we happen to have two kappa interacting Fock spaces, not necessarily for the same kappa, that are isomorphic, then there's a partial isometry between the occurring domains with the right co-kernel and the right range that intertwines the two different kappa. In particular, if one kappa is bounded, then so is the other. If one kappa is unbounded, then so is the other. So we cannot do something wrong by choosing a stupid kappa. And I should say also also the pre-Hilbert space can be different. They need not be to be on the same pre-Hilbert space. No. Okay. Now I'm happy to see that I have more time than I expected. So, are there urgent questions right now? Or? I don't see the chats, so otherwise
nothing
I would
in the chat so far.
Okay, I don't know if this is a good sign. So let us look at the subclass of interacting Fock spaces, so-called regular interacting Fock spaces, or POI, partially or positive operator-induced interacting Fock spaces. We go one step back in the history and go to the first definition of interacting Fock space, which is more or less the following by Accardi, Liu, and Wolovich. On the algebraic full Fock space, define a new semi-inner product. Of course, omega should remain a unit vector. Divide out the kernel. This gives a direct sum of pre-Hilbert spaces, and require that the usual creator here survives the quotient procedure. So this is the requirement, to have the creators here that turn the thing into an interacting Fock space, even based on this pre-Hilbert space H. If we start with this, then lambda is just the canonical map. And if we start with an interacting Fock space based on H, then we can recover a suitable inner product by this formula here. POI interacting Fock spaces, positive operator induced, are those where this here has a particular form, namely this. This is an operator that goes from the algebraic Fock space into its completion. And in order to make this a semi-inner product, it should be positive. Oh, I forgot. It should be a Fock map, of course. No? So even vacuum preserving map. No? So theorem, an interacting Fock space based on H is a POI interacting Fock space if and only if the canonical surjection has an adjoint going into the completion of the Fock space. No? This is what we call a regular interacting Fock space. No? Natural question. Okay, we have seen every interacting Fock space can be embeddably based. So the question is, can it also be regularly based? And the answer is a clear no here. Theorem, suppose we have a non-nilpotent interacting Fock space. By this we mean that all the Hn are different from 0. And choose just all degree 1 operators as creators. This we would call a full interacting Fock space. And a non-nilpotent full interacting Fock space can never be regularly based. And so regularity is an intrinsic property that does not depend on the basing. Now, we started with bounded sets of creators. So we can ask whether the creators are bounded, and we can ask whether the creator map, the whole thing, is bounded when we have a basing. Of course, well, either they are bounded or they are not. So the question is rather on the parameters we have. We have the kappa, we have the lambda or the L in the POI case. So for which of them do we get bounded sets of creators? Not sufficient is to have lambda or related operators bounded. Just looking at the 1 and the 2 particle sector is enough to get counterexamples. Sufficient is if kappa is bounded. If kappa is bounded, everything is bounded, but it's not necessary. Well, if we write down what it does mean that the creator A star X is bounded, or that the creator map is bounded, this is just spelling it out. So there's nothing new here, but we see that the responsibility for possible unbounded kappas is here in that the Hilbert space tensor product does not have the universal property of the projective tensor product, and every counterexample can be used to model a counterexample giving unbounded kappa. In the regular case, we can see what these conditions mean for the L, and we get this. These are inequalities of unbounded operators. And indeed, the Ln can be unbounded and still give rise to bounded operators. So this bounded is neither sufficient nor necessary. With kappa, we are up a bit better. And let me just show the last slide. This is about the class that has already been studied. Kappa should be a projection to come from a subproduct system. And this inequality shows that kappa is a squeezing, while this other inequality makes this product here well-defined. It's manifestly associative. And so this is the subproduct system structure, but my time is over. So I thank you. And here are some.
Well, thank you.